beyond light alone to things like neutrinos and gravitational waves to study the cosmos. Okay, so Kritika has brought this module wherein we are going to go over the most famous and basic forms of multi-messenger astronomy. We have a few terms that you might know or will get to know this time. We have neutrino astronomy, we have gravitational wave astronomy, and what other aspects we can look into in this field. Give me just a second. Yes, sorry. So let's begin. So first of all, we have a very obvious one because now it has become quite popular. But initially, what remained like constricted to only visual length astronomy, as we found out that light is an electromagnetic spectrum. So we have looked at the objects in the universe through all kinds of wavelengths. We can roughly classify them as radio waves, microwave, and infrared, ultraviolet, X-rays, and gamma rays. So, looking through objects through all these lenses, we can observe celestial objects under and get a lot more information about them than we can using just visual light. And a very famous example of this is the Crab Nebula in different wavelengths. So, as you can see, this is the Crab Nebula under radio waves, and this is it under infrared. So as you can see, there is a lot of difference. And as we go forward and look at it under different wavelengths, we can from the visible light, for example, we can see that there is an enormous gas cloud all around the nebula, which we were not able to figure out using the other previous two. And as we go forward in the ultraviolet as well, we can kind of make out there's a haze all around. And we also see there's something peculiar at the center of the nebula. So as we move forward and watch it under X-ray, we figure out that we can observe X-ray emission of a neutron star with a lot of high energy particles spread across it. So I think you should be able to see this like a tornado kind of a structure there. So this it's basically a neutron star. You'll learn more about the neutron star if you go through our modules. So the neutron star is basically spinning around its axis and it emits a lot of X-ray radiation through its poles, which gives us this kind of an image. And next we have the gamma rays. So again here you can observe that there is something we did not observe before that there is an immense source of gamma rays as well at the center. And all these things together, like obviously not just one fact can make me conclude that it's a neutron star. Uh, After we looked at all of these things and tried to figure out which object could have such kind of a characteristic, we figured that there is a neutron star at the center of the Crab Nebula. And which is pretty cool because if you look at the visible light photo, you would not really think much of what is at the center. It almost looks like it's just a gas cloud with colorful clouds surrounded it. So next up, we have neutrinos. So what exactly are neutrinos? They are the most abundant particles in the universe, and we did not even know about them for the longest time. So it's pretty cool. A neutrino is a subatomic particle that interacts only via the weak interaction in gravity. And because they are so small and they only interact via gravity, you can imagine that why they were undiscovered for so long, because they basically interact negligibly with any kind of matter. So they were also called ghost particles. Neutrinos are fermions. Basically, there are two basic kinds of subatomic particles, fermions and bosons. And neutrinos are fermions. You can read more about it in our module. And just for reference, when I say the most abundant particles, you can imagine about 4 million, there, you can imagine about 100 billion neutrinos pass through your thumbnail, like the nail of your thumb. You can imagine the size of it. And 100 billion neutrinos pass through it every second. So, yeah, they're really popular. But now that we know that they barely ever interact, so how will we, you know, detect them? So this is the reason they were undiscovered for so long, and now that they're discovered, it is still like a huge problem to detect them. And we're still in the process of getting better ways to detect them. But the most recent advancement here is the Ice Cube Neutrino Observatory. So this observatory is an underground facility in Antarctica, which is more than a kilometer under ice. So that is pretty isolated. Neutrino reacts with one of the water molecules, producing charged particle, electron, or muon. So we want to identify a neutrino getting like which is passing through the ice. So when it passes through the ice, there is a chance that it reacts with one of the water molecules, and we find this charged particle which reacts with light, emitting a bluish light, which is what we detect. We do not exactly detect the neutrino, but we look for a bluish light in the ice. So this is kind of the basic overview of how the Ice Cube Neutrino Observatory works. I would like to show you some animations for a better see. The upper layer is the ice, and in the lower layer, you can see as the neutrino passes through it, there is emission of light, and eventually we see a blue color, which is detected by the observatory in the form of detection of the neutrino. Hmm. And this is another short video about it. Uh, can you hear the sound of the video? Please tell me if you can hear or not.
No, not
Uh,
it.
o- okay, just a second, then I think I'll have to reshare. Yes, can you hear it now? Is it audible, guys?
जिज्ञासा, it isn't audible.
I was asking now. Okay. I This is difficult. I don't know. I think we'll have to skip. I'll put this video link in the group chat so that at least you can refer to it later because this is not there in the module or anything. Okay, never mind. So I'll tell you the gist of the video. They basically talk about. Wait a second, I'll reshare. Yes. So they basically talk about how. Yeah, basically talking about how Ice Cube Observatory detects a lot of neutrinos throughout the year. There was an approximation of around 100,000 neutrinos are being detected in the observatory in an entire year, which is a big deal. But the issue comes in the fact that we still cannot differentiate between neutrinos that are coming from different sources, and especially cosmic neutrinos, because cosmic neutrinos are basically the neutrinos that are coming from the early stages of the universe. And they would be pretty helpful for us to understand what the universe was like in the early stage. And out of the 100,000 neutrinos being detected, there are only like 100 neutrinos which are cosmic. So it's very difficult to distinguish between them. And also other sources, they talk about how there are two galaxies which we have as of now observed that emit neutrinos. And with the help of machine learning and a lot more technological advancements, we've also figured to detect neutrinos from our own Milky Way. So please watch the video, you'll get to know more about it. But coming to neutrinos from a specific source, the next one is going to be the most basic, the closest source of neutrinos for us. So I'll just begin with asking how much time does a photon produced in the core of the sun, this refers to the core of the sun, take to reach us? Like, just a guess, please, anybody. Okay, never mind. So we have uh, the obvious answer that we think of when we hear this question is 8 minutes, because we've studied from childhood that a photon takes 8 minutes to reach us from the sun to the earth. But there is a difference between the core and the surface. So, due to constant reabsorption and re emission of photons in the layers of the sun, when it gets produced in the core, actually, due to the nuclear fusion process happening, it actually takes them around 100,000 years to reach only the sun's surface. So once the photon has been generated at the center of the sun, we actually receive it after around 100,000 years. Although it is going to take only 8 minutes from the surface to Earth, but due to this constant reabsorption in the layers of the sun, we actually never really, get fresh photons, if you would like to call them that. Also, we have a very cool animation done by our animation team, which I would like to show you about nuclear fusion. Just a second. Yes, I hope you're able to see a sun. So we have this animation about the nuclear fusion occurring in the core of the sun. We can see there are two hydrogen molecules, hydrogen atoms, I'm sorry, that first of all combine to form deuterium, and then helium-3 nucleus is formed. And in the same way, we finally get the helium-4 nucleus, which concludes the process of nuclear fusion. And during this process, as you must have seen, I know the animation is pretty fast, but we can also observe how there are high amount of energy which is released, and there is a lot of other particles that are also released. So in this entire process, we also have neutrinos which are being formed. There are photons, obviously, which give us the light, but there are even more number of neutrinos which are being formed at the center of the sun every second, every moment, whatever. Yes. So now, which particles come out of the core of the sun and reach the surface quickly? I mean, I've clearly given the answer. We talked about how photons take so many years to reach us, and the photons that we receive are never actually going to, give us information about what's happening at the center of the sun because they're so old. And neutrinos, on the other hand, are only going to take 3 seconds to reach the surface of the sun because, like I said, they don't really interact with matter at all. Hence, when we receive neutrinos at the sun, at the earth, I'm sorry, uh, we basically receive fresh neutrinos, which we can use to extract information about the center of the sun. And these are called solar neutrinos, but obvious. And just these random trivia which I collected about these kind of neutrinos. Uh, the photons that we receive, this is to put in perspective that how much 100,000 years is. The photons that we receive right now today were actually produced in the Paleolithic era of the Earth. So you can imagine how redundant they are because they're basically giving us nothing about the center. And about 100 billion neutrinos pass through our thumbnail. And I'm sorry, I know I talked about this earlier, but uh, the 100 billion neutrinos is actually only the solar neutrinos which are passing through our thumbnails. And the most of the neutrinos which we receive at here at Earth are actually just solar neutrinos. Like I said earlier, we barely get any cosmic neutrinos, and uh, again from galaxies also, it's pretty rare for a neutrino to like land on Earth. Anyway, next up, okay, so we have a brief introduction to special relativity, which Vishwajit is going to take up.
Hello.
Yes, you're
Um,
audible.
cool. So, I mean, the next messenger we're going to talk about is gravitational waves. And before gravitational waves, we have to first obviously talk a bit about special relativity or relativity. So, as you guys know, uh, we have been using Galilean relativity whenever we solve the Newton's laws of motion problems that we usually find, or like whenever you want to make a car move. And that is that whenever even if I change frames between inertial frames, the time does not really change. So a 1 second in one frame is the same as 1 second in another frame. But as we know, when we go down this path and we develop our theory of when we develop our electromagnetic theory, we get in the end we get the fact that electromagnetic waves actually travel at a constant speed, which we call as the speed of light. And this speed is not really dependent on any source. So that also means that the speed is constant in every frame. This is actually a contradiction since uh, if we move from one frame to another frame, let's say the other frame was moving with some speed v, we know that the other speed will also decrease by the same amount, minus v. Uh, Hence, we scrap up everything we know and we work in another framework that we call as special relativity. That is, rather than time being the absolute thing, we take speed of light to be an absolute thing because till now it is not contradicting with anything else. And when I make speed of light as constant and go through with the calculations, I get another thing which is constant between different frames. And that is something known as space-time. Next slide. You guess? Thank you. So now what do I mean by gravitational waves, or what exactly is the thing that is waving? So under general relativity, that is a bit more inclusive version of special relativity, we know something known as space-time. And this gives us, since space-time is the one that is constant, at every point, the unit length actually changes. And this change in the unit length is the one that is actually waving. So at some point of time, 1 unit length in one point would be half a meter. And at another point in time, it might be 2 meters. And how these gravitational waves are actually formed is just like when moving electric charge, it produces ripples in the electric field. A moving accelerating mass produces ripples in space-time. And when two of such things, like two black holes or two supernovae or a neutron star and a black hole, when such massive objects come into close contact, they start rotating around each other. And this causes a lot of energy to be used up. As we know, E is equal to mc square, and when two masses actually, when two celestial masses get closer to each other, not all of this mass is being conserved per se. Some of it is being converted to energy, and this energy has to go somewhere. And most of it goes by light, and some of it also goes via this gravitational wave. And since these black holes and all of these objects are so far away, like the center of our galaxy is a supermassive black hole, and such objects are the ones which create such massive gravitational waves. Uh, these carry so much information about the origin and the nature of gravity itself. And another thing that is good about gravitational waves as to why we are using gravitational waves is light and all can be blocked by, let's say, the Oort cloud, which is surrounding our solar system, or other objects which are surrounding our solar system. But gravitational waves just pass through them. Hence, even if they are very far away and blocked by other stuff, the gravitational waves will pass through such objects and we can study those objects. Next, the video right now, I guess it's not working, so maybe I'll just put the link in the chat, or I'll just try if it works.
Yeah, this is also an audio video, like you'll have to need to hear it. So I think I'll just put the
Yeah.
link on the chat.
So yeah, just go to the next one. I guess this will also not work. Now, how do these gravitational waves actually get detected, or where do they get detected? So there is this, do you guess?
I can't
So
really
yeah,
hear you.
Is it breaking?
I mean, it was breaking for me. I don't know if my net is the problem, but it's fine now.
Okay, then. Yeah. As I was saying, so LIGO, that is Laser Interferometer Gravitational Wave Observatory, was actually created initially at two places, Hanford and Livingston. And the reason why they had created two was because these instruments are very, very sensitive and they didn't want any false positives. So they kept two at different places further away in the globe so that if compared to that small distance, uh, compared to the distance at which the black hole is actually merging, these 2 points are very close. So there would be no difference in the reading. But for disturbances like, let's say, an electric power outage or maybe some cars moving, those things will only be local. So such an error would only come under Livingston or Hanford, not in both of them. Yeah. So
Okay. We have another video, but this one is just animation, I believe. So I think
yeah.
it's fine.
So these are two black holes rotating towards each other. As we know, angular momentum has to be conserved. So as the black holes get closer and closer, they actually speed up. Now these colors that you see are actually just the brighter the color, that is more it's to the pink, the higher the peak. And since it's an image, we cannot actually just draw waves. So that's why we have used color coding here to like say the distance. So as you can see, like the gap between the two waves gets smaller and smaller, and that is because the frequency gets larger and larger.
This is a similar video of it. I think this one has sound. It basically depicts the sound of the two black holes merging. I think I'll send it.
So I think yeah, this video maybe I'll just put it on my phone so you guys can hear it. 1 second.
Yes, it's
So
audible.
were you able to hear that a raindrop sound? So this was the gravitational wave frequency mapped into the sound wave frequency, just to like visualize or audio visualize how it would have actually sounded. Now, let us talk about how exactly this machine detects gravitational waves. So here, LIGO actually, as the name suggests, uses lasers to measure the distance. Jigyasa.
I have the working of LIGO slide here. I think it's not culture. What can you see?
Yeah, I can see now. So yeah, uh, so basically there are two very long vacuum tubes in which a laser is passed. So now, as we know, the gravitational wave would actually shrink length, and we also know that the speed of light is constant. So in effect, what it does is it puts these two lasers out of phase. And since these lasers got out of phase, these would produce interference patterns. And based on these interference patterns, we can actually detect how much how much, depending on how much the interference pattern has been shown, we can determine how much the amplitude of the wave is. And this gives us how much energy is being produced by the gravitational wave and more information about the gravitational wave. Now, actually, these gravitational wave oscillations are so small that the actual change is just 10 to power minus 15 meters per meter. That is very small. That's smaller than an atom. But because these laser lines are around 10 kilometers, I think, so the cavity is very long. Hence, the change in the distance also becomes to a significant amount of the wavelength of the laser. And that is why we can see a interference pattern. So I think there's a YouTube video right after that. I don't think it needs an audio. Yeah. So this is
Uh,
obviously exaggerated movement. But yeah, so that is a beam splitter. So initially they are configured in such a way that there is no light in the end of the. So this plate that you can see is the sensor, and initially the sensor reading would be 0. And if there is any change in the lens, it would start to show some color or red light here. So yeah, that is how it gets detected. And again, since even though these are very energetic objects, these are very, very far away, as I've told. So why do we use this and how does that energy even come here? So every other thing that we have measured here, so for that instance, neutrinos or light, all of these actually fall down in 1 by r square because there is, let's say, some finite number of photons that are coming out, but they have to be uniformly distributed in a sphere in every surface. So it is actually 1 by area by 4 pi r square. So it is proportional to 1 by r square. But as we know, energy is actually directly proportional to the amplitude square. So the amplitude actually decreases only in a 1 by r fashion. And in gravitational waves, we actually just detect the amplitude of the wave, not the energy of the wave. Since what we are actually calculating is delta L, or the change in length, which is the amplitude. So using this method, we can actually capture events which have happened quite far away. Hence the motivation to use gravitational waves. And even though gravitational waves have been detected very early, gravitational waves are some of the results of general relativity back then. We had the equipment that we had to build had to be very sensitive, number one. And number two, it should not be sensitive towards noises. So to achieve that balance, it took some time. And finally, in 2015, we had our first observation of gravitational waves. So there's a bit more math in this, which you can find in the module.
Yes, so I think that is all for our presentation. Also about the videos that we could not see, I think I can just turn on the captions so at least you can read what's being said. Just a second. Okay, I think you should actually be able to hear it also now. It's audible.
Oh, can you? Yeah, I think it's audible.
Yeah.
Einstein is responsible for the theory of general relativity, which is a way of looking at the universe that has been proven out by observational evidence for the last 100 plus years. His basic tenet is that mass warps space-time, and that this can be observed, and that as in particular, massive objects spiral around each other, that they give out gravitational radiation or gravitational waves. This is ripples in space-time that is being caused by that mass interacting with space-time itself. So that leads to a tremendous amount of predictions. In particular, as binaries inspiral and collide with each other, we would see these waves rise to a peak and then ripple across the universe, and that they could even be detected if we had the right kind of technology to be able to feel or see or hear space-time itself moving. Gravitational radiation astronomy is developing detectors that can actually measure that change in space-time itself. Laser interferometry. This is the best way that we can actually measure this phenomenon. In 2017, a signal that was consistent with one of these gravitational wave increases and then decreases. We call it chirp. It gets bright and then it dies down. It looked like the prediction. But the fact that we saw a gravitational wave signal that was consistent with inspiraling neutron stars and a kilonova as a result. But kilonova is more energetic than a nova, less energetic than a supernova. At the same time, we saw a short gamma ray burst. That was great news, and it meant that we could take all the telescopes at our disposal and quickly point them at the location of the gamma ray burst. Hubble was called into the chase. Hubble images show us a very interesting galaxy and the location of that kilonova afterglow. So Hubble was able to show us what was happening in that position, tell us how bright it was, and importantly, pinpoint the location. It's telling us where it was happening in the galaxy. And not only is that giving us information about where it was in the galactic environment, but that's also crucial information for other telescopes to be able to point to that same location, and we can take that data and combine it into that multi-wavelength picture. As laser interferometry gets more and more power behind it and starts to see more and more of these objects, we are going to usher in the new era of multi-messenger astronomy. We're going to learn a tremendous amount about very rare events like kilonovae and other things that happen that give off gravitational waves that are going to allow us to just build more pieces onto that puzzle.
So as like I forgot to mention a point. So there are two observatories now, and more are being built. There's also one that is going to be built in India. That's very cool. And another reason for all of these observatories being built is so that we can pinpoint from where the gravitational wave is coming. So as we know, uh, based on the orientation of the gravitational wave, we can determine that it is coming from some general angle theta from the observatory, which actually spans out a circle. So it spans out a circle in the galactic sky. And the other observatory will also span another circle. And at the intersection of these two, there are 2 points. The gravitational wave came from one of these 2 points. And if we have more observatories, we can pinpoint directly from where exactly it is coming.
And this is the other video about neutrinos, which we could not watch earlier.
Deep in the Antarctic ice lies the Ice Cube Neutrino Observatory. Since 2011, it has been detecting light emitted from particle collisions in the Antarctic ice. An enormous number of neutrinos pass through the detector every second. IceCube detects 100,000 neutrinos per year that are created in the Earth's atmosphere. In contrast, there are only about 100 neutrinos arriving from the cosmos per year. It is difficult to filter these few cosmic neutrinos out from the rest, but so far there has been some evidence that two galaxies are emitting neutrinos. Researchers of the IceCube collaboration have now succeeded in filtering the large number of neutrinos with the help of machine learning. Neutrinos can now be found originating from the Milky Way. We are looking into the future of astronomy research. New machine learning methods and neutrinos can reveal information from places in the universe that were previously obscured by gas and dust. Independent researchers are modeling the distribution of neutrinos in the Milky Way. They expect to find particularly large numbers of these high-energy particles, where charged particles undergo acceleration in extreme magnetic fields and collide with other particles, presumably in star-forming regions, something that can be tested with IceCube data in the future. This observation established neutrinos as a new tool of astrophysics, which let us peer into regions of space from which light cannot escape.
Okay, I think those were all the videos that we weren't able to watch earlier. And about this video, I'd just like to add that it's pretty amazing how, this ghost particle, which went undiscovered and undetected for years, can give us so much more information about places we can't even really see because of dust and gases. And the similar thing applies for gravitational waves as well. So this is the basic point about multi-messenger astronomy, that we're not looking at objects just through the lens of light or the electromagnetic spectrum, but we're trying to figure out more ways in which the universe is trying to talk to us, kind of. And the instruments that we've built to really measure these messengers are pretty amazing. It's still in its like initial stages, and we've not like used it as much as I think there is potential. But it's quite amazing how we can, make such sensitive instruments to detect such out of the world kind of phenomenons happening in the universe. Sure, was there anything, any video which we could not see earlier? I think that was the only one now.
I think there was the audio of the black hole, but
But like I think everybody was able to hear it via phone.
yeah.
Yeah. So I think that is all about our presentation for today. The stage is open for anybody who has any doubts or would like to add anything to whatever we said today. And yes, from the gravitational wave video, it just recalled. I mean, if you've gone through science videos on YouTube, you must have come across this channel named Veritasum, and there's a very cool video about gravitational waves. We did not incorporate it here because it was pretty long and informative, but I would really recommend you to go watch it. And I mean, it's very cool to see the working behind LIGO and how, the scientists, the experience of the scientists that actually observed the first gravitational wave of the black hole merger in 2015. It goes around it. I would probably put the video link on in the chat as well. But yeah, it is very cool. Okay, seems like we don't have any doubts. So I think we shall conclude the session here then. Anybody who has any doubts is free to text us. Yeah, it's highly encouraged to, start doubts discussions on the Teams channel or WhatsApp group, whatever you wish. And again, I would just like to remind that this session was just for you to develop interest and for you to have an introduction about multi-messenger astronomy. But we would highly recommend you to go through the module which is uploaded on Teams, and I'm pretty sure you'll have a lot more fun reading that if you found this session intriguing. And apart from that, I would just like to announce some general things. We just put up the deadline for the basic modules today. They're to be submitted by this Sunday. And after this, we are going to have the assignments for advanced modules, which are going to be released soon. So I would kindly request you to finish up the assignments as soon as possible, because then you'll have advanced assignments as well. And again, just a reminder that the assignments are compulsory for the certification. All the basic modules assignments, and for advanced modules, you have to cover 4 out of the 7 advanced modules which are being provided for resume verification. And yeah, that's all. So I think we shall conclude the session here. Thank you for joining.